Good morning, everyone. This is my commentary to sustainability modeling lecture number 10. This is a lecture on water management, and it's the first of the lectures in which we start tackling societal issues that are integrated in a way not application specific, but more we're going to be moving more into general types of models that could be tailored to particular situations. Water management is going to be the first of these topics, and as you saw in the lectures and also in the structure of how the Vensim model is assembled, you know, it is quite a complex model, and I'll go back to something I said at the beginning of the class, that you know, modeling sustainability issues is as much as a science as it is an art, and if you look at the structure of the model and the variables and the way they're formulated, you'll notice that there's probably a combination of three things going on, or three sources of information that get assembled into the model. I think the first one has to do with scientific laws and or theories, and these are fairly well established concepts that you can refer to in the literature, or they're established concepts of knowledge, conservation of mass. So no matter what we do with a water management model, the volumes of water have to add up. So that's a fundamental principle. We cannot get away from doing that. Okay. However, that's not the whole story. Water management involves assimilating data that may exist, data on, for example, usage of water per person, or usage of water on specific activities, agriculture, industry, like how much water does a specific crop in agriculture use per unit month or per unit year. So this type of data needs to be collected and needs to be assimilated into the model, and it's far from being a fundamental issue. It's more specific. Then the third piece of information you may have is what happens when you have no information on something, or you need to make an assumption, and this is what I call placeholders. It's assumptions that you make when you have no data, you have no information, but you need to make an assumption to make your simulation work and give you some results, and doesn't mean that you're going to be right. Very likely you're not going to be right, but it does allow you to close the loop and run a model, get some results, and assess your results, and then come back maybe to that assumption, collect more data, invoke other principles, and redo this. So system dynamics modeling, and particularly with sustainability issues, we tend to be very cross-disciplinary, and it tends to involve multiple aspects of life. It's a highly iterative process. It's what I call it's evolutive modeling. It's models that need to evolve over time, and I think in that sense, I can appreciate some comments that I've received from students. I think they're very legitimate about things like, well, how do I know that this is the way a model is put together? I think the quick answer to that question is that you don't. I think the best answer you can hope for is that you take the different modeling experiences that we've done in this class and that we'll continue to do in this class, and try to learn some tips and tricks of the trade, because there are tricks that you can use, and use some of the formulations, learn from each model, look very closely at how the models are structured, how the different nuances are formulated. This water management model that we talked about in the class, SIWA, has a lot of these particular issues that come into play. For example, what happens when you have this difference between the sources of water and the supply. What happens, how is water consumed? We know there are leaks, so there has to be some efficiency in that transfer. So what is that efficiency? What does it mean? Right now, you sort of make an assumption. The efficiency is 70%, and you run with it, and you may need to come back with it if you don't have that data. If you do have that data, you can put it in, and then you may not have another piece of information, and you really run these in a highly iterative and evolutive fashion. I think the other piece that is also important to realize is that models like CWA, which is actually fairly simple once you get a handle on it, but this is not the creation of an individual person. It's really a creation of it's a collaborative effort, and I think that's the other piece that I wanted to emphasize. Some of these efforts, although I'm teaching you a very condensed version in this class, and I do expect you individually to understand what's going on. I don't think I expect you individually to develop a model of this complexity. That would be unrealistic, so I think the best I can tell you in that respect is that for you to understand that modeling is not an end; it's really a path. And I think you need to. The idea of this class is that you sort of understand that concept first, and second, that you learn some of these little approaches that there are to fine tune and integrate these issues. Because when you're integrating, scientific and physical laws from different disciplines with data, empirical data or experimental data that may be along the way, and also some of these assumed relationships that you have to, some assumptions you have to make. It's it can get pretty messy very quickly. So so there's no easy answers and there's no single solution. I think the important thing is that you're able to distill and synthesize all this information into a formulation that makes sense. And if you achieve that, then you achieved a lot. And that's the level of synthesis and the level of effort that I would expect for the term paper. So if we go to the subject of the second assignment, I want you to be able to synthesize a formulation for a problem. Okay, and it doesn't have to be the formulation. It doesn't have to be the best formulation. But it has to address the problem, and it has to be well rationalized. So I do expect you to really, this is a highly intense thinking exercise, and I really want you to think. So this is not something mechanical. It's not like, okay, I'm going to start putting boxes and arrows and things are going to work out magically. That's not going to work, as you know. This is really about, well, let's think about the logic about how the system that you approach, how do I think it works, okay? And then translate that thinking into the Vensim format. Along the way, you're going to have to make some assumptions about data that you may have, data that you may not have. You're going to have to bring in some fundamental principles, and you're going to have to mix them up. Okay, so what I expect you to do is to give a shot to that level of synthesis. That's far from being trivial, because it's really a different type of thinking. For those of you that have been trained in the sciences and engineering and even in the humanities, you're taught to think in a very structured way. This is really about trying to break a little bit those structures, and not for the sake of just breaking them, but also integrating and synthesizing across them. And that's a transformational effort that you need to make. So that's why that's the reason I created this class, and that is I think that's the primary objective, the primary learning objective that I have for you. So I'll stop blabbering about this, because I think you've gotten the message. I have included in the class directory, in the lecture directory for this, in the Dropbox folder, the lecture, of course, the lecture itself, and a video for the lecture and a video for the CWA model. I also included some interesting readings. There's a couple of system dynamics models that I'd like you to look at. One for Nevada, which is for pretty arid region, and the other for South Florida, which is a pretty humid region. And it would be nice for you to look at the structure of the models and also the logic that's built behind it, because there's different problems. In South Florida, you're dealing mostly with avoiding floods because there's too much water. In Nevada, you're actually trying to make the most of the water you have. So it's two different problems. They are both water management issues, but they're very different. Okay, and the models are different, and the logics are different, and so there's really no model is unique. This is I always make the analogy: the system dynamics model is like, it's like fashion design. It's like clothing. There's no two pieces are the same. There's no mass production. Okay, here, there's only tailored, individualized approaches, and even in that case, they're never going to be unique. So I think that's really important. System dynamics is it's a contact sport. It's a trial by fire discipline. So hopefully you're enjoying the ride so far. Let's see. Oh, I also included a video that I liked about a recent lecture that a professor gave recently about innovation, and I think a lot of the messages that are in that video, and I encourage you to see it, are highly applicable to this class and also to practitioners and professionals in the sustainability field. I think a lot of it in sustainability is about really integrating, collaborating, which some of the messages that are there, and some of the messages that I think are applicable to the learnings of this class. So I'll leave it there. I hope you enjoy your week, and I'll see you next time for Lecture 11. Take care. Have a good week.